In this paper, we introduce a pipeline that can be used in non-line of sight imaging scenario to reconstruct object shape. Unlike most previous work on this problem, which focused on reconstructing volumetric representation of the object, our pipeline directly optimizes the surface of the object, enabling high-detail reconstructions. By non-line of sight imaging, we refer to the problem of reconstructing parts of a scene that are not directly visible to the sensor. We will be focusing on the so-called looking around the corner setting, shown here. We use a laser to illuminate a point on a visible surface, such as a wall, and measure light transport using a time-of-flight camera. Our objective is to recover the non-line of sight surface S by considering photons that reflect between the visible and non-line of sight surface before reaching the camera. Before we introduce our reconstruction pipeline, first let's look at the image formation model for the looking around the corner setting. The sensor gathers radiance reflected on all points on the non-line of sight scene. From radiometry, we know that we can express the resulting measurement as an integral of a function g evaluated on points on the surface S. G is a function of surface point location, surface normal, visibility, and BRDF. Instead of using this radiometric model, most prior work relies on an approximation, which represents the non-line of sight scene not as a surface, but as a so-called albedo volume of semi-transparent isotropic reflectors. Under this model, the measurements of the sensor can be written as a volume integral, accumulating contributions from all voxels in the scene. This model is mathematically convenient and can be evaluated and inverted using simple linear algebra. However, it is inaccurate, as it does not account for effects such as surface shading, normal, and reflectance. In this work, we use the physically accurate radiometric model to develop an optimization framework for directly recovering the non-line of sight surface, as well as its reflectance. We focus here on surface recovery and show more details about reflectance in the paper. We use a triangular mesh to represent the non-line of sight surface. Our goal then is to find a mesh that can be used to reproduce our transient measurements. To see how we can do this, we make two observations. First, as we already mentioned earlier, the measurements we collect can be expressed as an integral over the surface of the mesh. Not only that, but as we prove in the paper, the same is true for the derivatives of these measurements with respect to the mesh vertices. Second, even though these integrals cannot be evaluated analytically, they can be efficiently approximated using Monte Carlo rendering. When estimating derivatives, this is often referred to as differentiable rendering. Therefore, we can combine differential rendering with stochastic gradient descent in order to evolve the mesh so that it fits the data. This works as follows. Given an initial mesh, we first use Monte Carlo rendering to estimate the measurements and their derivative with respect to the vertices of the current mesh. We then use these derivatives to form gradient vectors that tell us how to update the vertex locations of the mesh. Finally, we repeat this process until convergence. Here, we show some of our results. We show ground truth, the initial mesh, and our reconstruction results. During the optimization, we not only update the vertex locations, but also increase the mesh resolution. Please refer to the paper for more details. Here we show another result. We can see that the text on the SOAP becomes legible after optimization. Here we show a complex scene where the object is very non-convex. The surface contains a lot of details. We can see that through our optimization framework, we can recover a lot of details of the scene. Here we show more results. Thank you.